Hello, welcome back. Guys, I'd like to continue on chapter 2. Chapter 2 is a very brief chapter that we like to give some revision on some of the basic concepts in statistics. Like we mentioned earlier, that in statistics or in sample survey, we always ask ourselves, what is the purpose of conducting the sample survey? We need to set our objective. So the objective of statistics is to describe about the population, making use of some of the information that we collected from the sample, like the mean, that the average that we always talk about. Another measurement is the median. Median is the middle value in the list of the data. So if we collect a set of the data from the sample, we arrange that we rank them from the smallest to the highest, and then the numbers that stand in the middle would be the median. Mode would be another measurement to talk about the parameters. The mode is the value that occurs the most often. So again, you look at the set of data that you collected, the data that appears most often would be the mode. So these are three statistical measures that help us to analyze the central tendency of the data. When we have a symmetrical bell-shaped normal distribution, then the mean, the median, and the mode would be equal. Other measurement we like to make use of to describe about the population would be the proportion or the total. The next step, we're going to ask ourselves, what is the influences about the population from the information that we get contained from a sample? What sampling scheme we are going to use. Basically, we would decide which sampling scheme by the minimized variance that we can calculate it. So out of the 4 sampling schemes we mentioned in chapter 1, like the simple random sampling, stratified random sampling, systematic sampling, and cluster sampling, we can calculate the estimated variance of each of the sampling scheme. The smaller of that would help us, likely give us higher evidence of choosing that sampling scheme because of the less of the errors. After selecting the parameter, after determining which methods we're going to measure the sampling scheme, then we also introduce the concept in the interval estimation. So one point of the estimate, like the mean, is only a point estimate to talk about the population. But the best as a statisticians, we like to talk about what is the probability of that estimate. It's good to picture the population, so we will give a confidence interval of our prediction from the goodness of fit. So we'll come back to all this concept later on. In statistics, usually the statistic theory, we would assume the population are in infinite size. So let's look at this example. Suppose we have a large number of integers in our populations. Let's go from 0 to 9. Okay, so look at this is a relative frequency table of the population from 0 to 9. If we randomly choose any integer between 0 to 9 with replacement, that means every time I choose an integer, it would have a probability of 0.1 to be chosen. So this would be a population of infinite case if I choose any number with replacement. The probability of the distribution of the random value y equals to 0.1 in this case, if I let y being the chosen number. Okay, so each of the integer would have an equal random probability to be chosen. They all equals to 0.1. Then with that case, the expected value of a chosen variable y will equals to the summation of that chosen value multiplied to probability of being chosen. So that's equals to mu. For example, look at this infinite population case. The expected value mean would equals to the probability multiplied to each of the value being chosen. So in this population, the mean value is 4.5. Then we also want to describe about the variance. But the variance is defined as the variability of the measurement of the populations. It is defined as the expected value of the square of the deviation between the chosen value y to the mean value. So in this case, we calculate each of the expected value of the value of y minus the mean value, or each of the chosen value minus the mean value taken square multiplied to the probabilities of that variable y being chosen. In this case, the variance of the population, this is the true value of the population variance, is 8.25. Standard deviation is defined as the square root of the variance. So in this case, the population true variance is equal to 2.92. So throughout the course, we talk about the population true value. So mu would be used in the notation to represent the true value of the population mean. Sigma square would be the true value of the variance for the population. Sigma would be the true value of the standard deviation of the population. Okay? Then comes to the sample survey. Since we can't do a consensus all the time, so we cannot collect all the data from the population for most of the time, then we can only select a sample and then look at the parameter of the sample to estimate the populations. For example, we want to select a sample of size n, little n measurement, and we look at the sample. We use the sample mean to describe about the population mean, so as we use the sample variance to describe about the population variance. So the characteristics of the population would be inferred from the sample. Sample mean, usually we use the notation y bar, little y bar, to represent the sample mean, which equals to summation of all the value we collected from the sample divided by the sample size. The sample variance S squared equals to each of the yi data we collected from the sample subtracted to the mean, taking square, and then add them up together divided by n minus 1. So n minus 1 denotes that this is a sample variance. So back to our example, the infinite population example, from 0 to 9, if we choose the sample size of 6 with replacement from the population, then we can choose a sample. For example, we can choose 693,880. Pay attention to the replacement. With replacement in this case, that means each of the number being chosen from the population, every time we have the population size of 10 digits, 10 integers being chosen. So with replacement, each of the integer would be chosen at equal probability of 0.1. So we can see that, especially referring that integer 8 being chosen twice, because every time we choose the sample from the populations of size from 0 to 9. Okay, so in this case, we can calculate the sample mean equals to 5.667. We can calculate the sample variance, which is 12.2667. From the essential limit theorem, we can say that if we repeat the sample many times, that we choose 6 samples from the population with replacement, then we can have a distribution of the y bar, or the sample mean. In this case, the expected value of our sample mean would be an unbiased estimator for the population mean. In the infinite population case, the variance of the y bar, or the distribution of our sample mean, would have a variance that equals to sigma square over n. Assuming that we know the population true value of sigma square, then the variance of our sample mean would be equals to sigma square over n. And s squared from our sample, the sample variance, is actually form a reasonable approximation to the population true value sigma square. So by the central limit theorem, again, the estimated variance of our sample mean will equals to s squared over n. Okay? So this distribution explains about our example. So from one sample that we choose, we have one value of y bar, which is 5.667. S squared is 12.2667. So if we theoretically, if we repeat choosing the sample many times, like this, if we perform 50 sample means, so if we repeat choosing n samples, 6 samples from the infinite population 50 times, then we would obtain 50 y bar. Then we can plot it out. Now we have a distribution of the sample mean. Like the central limit theorem says, the expected value of y bar would be the unbiased estimator for the population mean. In this case, we can look at that 50 sample means. It looks like the one in the middle, 4.5, would be an unbiased estimator for the sample mean. Then we look at the variance of our sample mean. We can use the s squared divided by n to describe about the estimated variance of my sample mean. Okay?